Hello there, and welcome to Science Documentary for Sleep. In this long-form documentary, I'll be spending time with some of the calmer, steadier ideas inside quantum physics. This is not a lesson to complete or a puzzle to solve. It's simply a place where accurate science can unfold at an unhurried pace. You're welcome to listen closely, or loosely, or somewhere in between. Nothing here needs to be memorized, and understanding doesn't have to arrive all at once. Sometimes it settles gradually, like a landscape becoming clearer as light changes. I'll be here as a steady presence, guiding the ideas gently, without pressure or performance. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you'd like, you can also share where you're listening from and what the local time is for you. Let's begin. As we settle into this first segment, nothing has shifted yet. We're simply continuing from the gentle arrival you've already made. Imagine standing at the edge of a very large map, not a political map or even a geographical one, but a map of scale. On one end, there are mountains and oceans. On the other, distances so small they almost resist imagination. Quantum physics begins at that far end of the map. It is the study of nature at extremely small scales: atoms, electrons, and the even smaller structures beneath them. At these scales, matter and energy do not behave the way everyday objects do. The familiar rules that describe falling apples or moving planets stop giving reliable answers. This isn't because reality becomes chaotic. It's because different rules apply when size becomes very small. Quantum physics exists to describe those rules accurately. For you, as a listener, this matters quietly. It explains why the world feels solid and predictable, even though its foundations are described by unfamiliar mathematics. You don't need to hold that tension. We can simply let the scale remain vast and move forward gently from there. With that sense of scale still present, nothing new needs to be added yet. We're still standing near the same map, just looking a little closer. Picture a calm shoreline made of fine sand. From far away, the surface looks smooth and continuous. Up close, it separates into countless individual grains. One of the core discoveries of quantum physics is that energy behaves like those grains. At very small scales, energy does not flow smoothly. It comes in discrete packets called quanta. This idea was first introduced to explain why heated objects glow the way they do. Energy, in quantum physics, can only be exchanged in specific amounts. There are no in-between values. An atom cannot absorb half a quantum of light. It either absorbs one or it doesn't. This fact matters because it sets a fundamental texture to reality. The universe is not infinitely divisible in its actions. For you, this explains why atoms are stable instead of collapsing. It also quietly supports every electronic device around you. We don't need to push further yet. The idea can rest here, complete and intact. That granular picture still holds as we move gently onward. Nothing has been left behind. We're only changing perspective. Imagine a dark room where a single beam of light enters through a narrow gap. Dust drifts slowly through the air, revealing the beam's path. In quantum physics, light carries energy in quanta called photons. A photon is not a tiny solid particle, but it also isn't a smooth wave in the classical sense. It behaves as both, depending on how it is observed. This dual behavior is not metaphorical. Experiments show that light can create interference patterns like waves, yet arrive at detectors as individual, localized impacts. This matters because it forces physics to abandon simple categories. Light is not either a particle or a wave. It is described by mathematical rules that allow both behaviors. For you, this explains why intuition sometimes fails at small scales. Nature is consistent, even when categories blur. There's no need to resolve that tension now. It can remain open and surprisingly calm. With light still in view, the setting remains steady. We're not changing direction, only deepening focus. Picture a quiet experiment running over many hours. A detector waits patiently, recording tiny flashes one by one. In quantum physics, measurement plays a unique role. Before measurement, certain properties like position or momentum are described as probabilities, not fixed values. The act of measurement forces one outcome to appear. This does not mean consciousness alters reality. It means interaction does. When a quantum system interacts with a measuring device, the system and device become physically linked. This fact matters because it replaces certainty with structure. Quantum physics does not say anything can happen. It says outcomes follow precise statistical rules. For you, this reframes uncertainty. It is not ignorance, but an intrinsic feature of nature at small scales. That idea doesn't demand resolution. It simply sits, quietly stable, as we move on. Nothing has been lost as we continue. We're still inside the same experimental calm. Imagine trying to track a small fish beneath clear water. The more sharply you focus on where it is, the harder it becomes to judge how fast it's moving. This image echoes the Heisenberg uncertainty principle. In quantum physics, certain pairs of properties, most famously position and momentum, cannot both be known precisely at the same time. This is not a limitation of instruments. It is a property of nature itself. The more precisely one quantity is defined, the more spread out the other becomes. This matters because it prevents quantum systems from behaving like rigid objects. It stabilizes atoms and prevents electrons from spiraling inward. For you, this explains why matter has size and structure. Uncertainty is not disorder, it's balance. We don't need to push that further. The balance holds quietly on its own. That balance carries us forward without effort. No new footing is required. Picture an electron not as a dot, but as a soft cloud surrounding an atomic nucleus. In quantum physics, particles like electrons are described by wave functions. A wave function does not show where a particle is. It describes the probability of finding it in different places. This probability cloud has shape and structure. Electrons occupy specific energy levels, forming orbitals. They do not move in neat planetary paths. They exist as distributed patterns governed by mathematics. This matters because it explains chemistry itself. The shapes of these probability clouds determine how atoms bond. For you, this means the solidity of objects emerges from overlapping probabilities, not rigid components. That may sound abstract, but it isn't fragile. It holds together the physical world reliably. We can let that realization remain unforced. As this first segment continues, nothing needs closing. We're simply arriving at another quiet view. Imagine countless atoms arranged into a familiar object, a table, a stone, a resting hand. Quantum physics does not replace classical physics. It underlies it. When large numbers of quantum systems interact, their collective behavior averages out uncertainty. Classical laws emerge naturally at human scales. This matters because it explains why everyday life feels stable. Quantum effects are still present, but they cancel and blend into predictability. For you, this means there is no hidden conflict between quantum strangeness and daily experience. They are part of the same continuous description of nature. We don't need to draw conclusions yet. The continuity speaks for itself, and from here, the landscape can continue unfolding slowly and without pressure. Nothing from the previous segment needs to be set aside. The ground we're standing on remains steady and familiar. Imagine a wide field at dusk. The air is still, and movement is subtle enough that it only becomes noticeable when you pause to look. Quantum physics often describes systems as existing in superposition. This means a quantum system can occupy multiple possible states at once until an interaction forces a single outcome. An electron, for example, is not in one position or another beforehand. Its state includes all allowed possibilities together. This is not a metaphor or a trick of language. It is a direct consequence of how wave functions evolve over time. The mathematics treats all possibilities as simultaneously real within the limits of probability. This matters because it expands what state means in physics. A system is defined by potential, not just actuality. For you, this softens the idea of definiteness. Reality can be structured without being singular. That idea can rest here without effort. With that openness still present, we continue without strain. Nothing has changed direction. Picture two coins resting under separate cups on a table. They appear independent, with no visible connection. Quantum physics introduces a phenomenon called entanglement. When particles interact in certain ways, their properties become linked, even when separated by distance. Measuring one particle instantly constrains the possible outcomes of the other. This does not involve signals traveling faster than light. No information is transmitted in the usual sense. Instead, the system must be described as a single combined whole, no matter how far apart its parts move. This matters because it challenges the idea that physical systems are always locally independent. Nature can be correlated more deeply than distance suggests. For you, this reframes separation. Connection can persist without communication. There's no need to resolve how that feels. The fact stands quietly on its own. That sense of connection remains as we move forward. Nothing has been undone. Imagine listening to a chord instead of a single note. Each tone has meaning, but the harmony matters too. In quantum mechanics, entangled systems are described by a shared wave function. The system's properties cannot be reduced to independent descriptions of each particle. Only the whole is fully defined. This is why measuring one part immediately limits the outcomes of the other. The description was always collective. This matters because it forces physics to treat relationships as fundamental, not secondary. The structure of reality includes correlations at its base. For you, this suggests that isolation is not always the default. Some systems exist only as relationships. That thought doesn't need emphasis. It can remain as quiet harmony in the background as we continue onward. The field of view stays wide and calm. We are still following the same landscape. Picture a set of faint ripples spreading across water. They overlap, reinforce, and sometimes cancel. Quantum systems evolve according to a precise equation, the Schrödinger equation. It describes how the wave function changes smoothly over time. This evolution is fully deterministic. Probabilities shift predictably until measurement occurs. There is no randomness in this evolution itself. The uncertainty appears only when outcomes are selected through interaction. This matters because it corrects a common misunderstanding. Quantum physics is not chaotic underneath. It is orderly, but probabilistic in expression. For you, this means uncertainty coexists with lawfulness. Both are present without conflict. That balance doesn't ask to be resolved. It simply continues, steady and intact. Nothing has accelerated as we proceed. The pace remains intentionally even. Imagine a narrow slit cut into a barrier. Beyond it, a surface waits quietly to record impacts. When particles like electrons pass through such slits, they form interference patterns over time. Each particle arrives as a single localized event, yet collectively, they build wave-like structures. This demonstrates that probability waves guide outcomes, even when particles are detected individually. The wave function influences where events are likely to occur. This matters because it shows that probability is not mere guesswork. It has physical effects that shape patterns. For you, this offers reassurance. Randomness in quantum physics is structured, not arbitrary. The image can fade gently now. The pattern has already been formed. As we continue, nothing needs to be summarized. We are still moving through the same ideas. Picture a system slowly interacting with its surroundings. Minute exchanges of energy accumulate over time. Quantum systems rarely exist in complete isolation. When they interact with their environment, their quantum properties spread outward. This process is called decoherence. Decoherence explains why quantum superpositions are not observed at large scales. The environment effectively records information, making outcomes appear classical. This matters because it bridges quantum and everyday physics. It explains how definite outcomes emerge without requiring collapse by observation alone. For you, this restores continuity. The strange does not replace the familiar, it fades smoothly into it. That transition doesn't need attention, it happens naturally and reliably. The path remains open as we reach this point. Nothing here needs closing or completion. Imagine countless interactions happening constantly: air molecules, light, thermal motion. Quantum effects are always present, but they are usually masked by decoherence. Only carefully controlled systems preserve their quantum behavior long enough to observe. This is why quantum experiments require isolation and precision. It is not because quantum effects are rare, it is because the environment overwhelms them so easily. This matters because it reframes strangeness. Quantum behavior is not exotic, it is simply delicate. For you, this means the quantum world is not distant or separate. It is here, continuously, beneath ordinary experience. We don't need to linger on that realization. The presence is constant, and we can move forward without effort. Nothing from the earlier segments needs to be carried deliberately. The ideas are already moving on their own. Imagine a laboratory that hums quietly through the night. Machines wait, lights stay steady, and time stretches evenly. Quantum physics introduced a shift in how predictions are made. Instead of predicting exact outcomes, it predicts distributions of outcomes. These predictions are remarkably precise. When experiments are repeated many times, the results align closely with quantum calculations. This statistical accuracy is not a compromise. It is the core strength of the theory. Quantum mechanics does not fail to predict details. It predicts the correct pattern of results every time. This matters because it anchors quantum physics in experiment. Its claims are not philosophical guesses. They're repeatedly confirmed by measurement. For you, this establishes trust. The quiet strangeness we're describing rests on one of the most tested frameworks in science. There's no need to reinforce that further. The reliability is already built in. That sense of reliability remains as we continue. The setting has not shifted. Picture a long series of identical experiments, each one beginning the same way. In quantum mechanics, identical preparations do not guarantee identical outcomes. Instead, they guarantee identical probabilities. Over many trials, those probabilities reveal themselves with clarity. This means quantum events are individually unpredictable but collectively stable. The theory does not predict which specific outcome will occur, only how often each outcome will appear. This matters because it reshapes the idea of causality. Cause and effect still exist, but they operate through likelihood rather than certainty. For you, this allows room for variation without sacrificing order. Nature remains dependable, even without exact repetition. That balance doesn't require effort to hold. It stays steady on its own as we move gently onward. Nothing has been left behind. We're simply changing vantage points again. Imagine a spinning coin caught mid-air, not yet heads or tails. In quantum systems, outcomes are not hidden in advance. There is no underlying value waiting to be revealed. Experiments testing this idea show that certain properties do not exist until they are measured. This distinguishes quantum uncertainty from classical ignorance. It is not that information is missing, it is that the property itself is undefined beforehand. This matters because it challenges older assumptions about realism in physics. Nature does not always assign values in advance. For you, this invites a softer view of definiteness. Not everything must exist fully formed to be real in a meaningful way. That idea doesn't need agreement or resistance. It can remain simply present as we continue. The pace remains unhurried. The landscape is still familiar. Picture a complex equation written across a chalkboard. Symbols interact with precision and restraint. Quantum mechanics relies on linear mathematics. Wave functions can be added together, forming new valid states. This linearity allows superposition to exist mathematically. Because of this structure, small changes combine predictably. Quantum systems respond smoothly to influences until interaction selects outcomes. This matters because it explains why quantum calculations scale so reliably. The underlying mathematics is stable and consistent. For you, this reinforces quiet order beneath complexity. The unfamiliar behavior rests on familiar mathematical discipline. There's no need to inspect the equations themselves. Their steadiness is enough for now. We can move on without carrying the symbols with us. Nothing has become more demanding. We're still within the same calm frame. Imagine energy levels stacked like shelves, each one distinct and evenly spaced. In quantum systems, energies are often quantized. Electrons in atoms can occupy only specific energy levels. Transitions between levels involve absorbing or emitting quanta. These discrete levels explain atomic spectra. Each element emits and absorbs light in a unique pattern. This matters because it allows scientists to identify elements across vast distances. The composition of stars is known through these quantum signatures. For you, this means quantum rules reach far beyond laboratories. They quietly describe the makeup of the universe itself. That reach doesn't need emphasis. It extends naturally, without effort, as we continue onward. The view remains wide and steady. Nothing needs to be summarized. Picture a particle confined within a small region, unable to escape beyond invisible boundaries. Quantum confinement occurs when particles are restricted to very small spaces. Their allowed energy states shift as a result. Smaller confinement leads to higher energy spacing. This effect appears in nanoscale systems like quantum dots. Their optical properties change with size alone. This matters because it shows how geometry directly shapes quantum behavior. Size becomes a controlling parameter. For you, this reveals how precision engineering can harness quantum rules. Structure itself becomes a tool. That realization can remain quiet. The relationship between size and behavior is already complete. As this segment continues, nothing closes. We are simply arriving at another stable point. Imagine layers of explanation resting atop one another, each one supporting the next. Quantum physics does not remove meaning from the world. It replaces rigid certainty with structured possibility. Its predictions are exact in form, even when outcomes vary. This matters because it preserves coherence. Reality remains intelligible, even when intuition must adjust. For you, this offers continuity rather than disruption. The world you experience emerges smoothly from deeper rules. We don't need to resolve that emergence now. The structure holds quietly beneath experience, and from here, the understanding can continue unfolding slowly and without pressure. Nothing from earlier needs to be recalled deliberately. The ideas have already settled into place. Imagine a calm laboratory where time is measured carefully. Clocks tick evenly, marking moments without drama. In quantum physics, time plays a different role than position. time is not represented by an operator in the same way. Instead, it enters the equations as a parameter that guides how systems evolve. This means quantum mechanics describes change in time, but not time itself as a measurable quantity like energy. The flow of time is assumed, not quantified. This matters because it sets limits on what quantum theory attempts to describe. It focuses on how states change, not why time flows. For you, this distinction softens expectations. Not every aspect of experience is treated symmetrically in physics. That asymmetry doesn't create instability, it simply defines the scope, and we can continue calmly within it. With that sense of scope still present, the view remains steady. Picture a system prepared carefully, its conditions set with precision. In quantum mechanics, initial conditions fully determine how probabilities evolve. Once a wave function is specified, its future development follows exact rules. There is no ambiguity in this evolution. The uncertainty lies only in which outcome appears, not in how probabilities are calculated. This matters because it preserves predictability at the level quantum theory is designed to address. The framework remains complete and self-consistent. For you, this reinforces quiet confidence. The theory does not wander once defined, it proceeds with clarity and restraint. That steadiness doesn't ask for attention, it remains quietly reliable as we move onward. Nothing needs to be added yet, we're simply shifting perspective again. Imagine watching ripples reflect off the edges of a pool. Patterns emerge from boundaries alone. In quantum systems, boundary conditions strongly influence allowed states. A particle confined within a region must adopt wave patterns that fit those limits. This is why confinement creates discrete energies. Only certain standing wave solutions are permitted. This matters because it ties physical behavior directly to constraints and geometry. The environment shapes what is possible. For you, this highlights a quiet principle. Limits do not merely restrict behavior, they define it. That idea doesn't need elaboration. The influence of boundaries is already clear enough to carry forward. The pace remains unchanged. We're still within the same conceptual space. Picture two paths converging toward a single outcome. Each path contributes quietly to the result. In quantum mechanics, probabilities arise from combining probability amplitudes. These amplitudes can interfere, reinforcing or cancelling one another. This interference is responsible for many quantum patterns. The probabilities are not added directly. Their underlying amplitudes are. This matters because it explains why quantum outcomes depend on phase relationships. Subtle differences create visible effects. For you, this reveals a deeper layer of order. Outcomes reflect hidden structure, not randomness alone. That structure can remain unseen, its influence is already present as we continue. Nothing has shifted abruptly, the continuity remains intact. Imagine energy flowing between systems in small, deliberate exchanges. In quantum interactions, conservation laws still apply. Energy, momentum, and other quantities are conserved exactly. Quantum mechanics does not relax these principles. It incorporates them into its formal structure. Allowed transitions respect these constraints fully. This matters because it preserves continuity with classical physics. The same conservation rules apply at all scales. For you, this maintains coherence. The deeper description does not contradict the familiar one. There's no need to dwell on that harmony. It exists naturally, supporting the larger picture. The scene remains calm and unforced. We are still moving evenly. Picture a system exchanging information with a measuring device. In quantum physics, measurement outcomes are registered through physical interaction. The measuring apparatus becomes part of the system. This interaction leaves a tracer record that cannot be reversed easily. That irreversibility gives outcomes their permanence. This matters because it explains why measurements feel definitive. They are embedded in physical processes. For you, this grounds abstraction in material reality. Nothing mystical is required for outcomes to become fixed. That grounding can remain quiet. The explanation stands without effort as we move on. As this segment continues, nothing asks to be concluded. Imagine a long chain of interactions, each one following from the last. Quantum physics describes local interactions precisely. Each interaction obeys quantum rules. Large-scale behavior emerges from accumulation, not exception. This matters because it preserves continuity between scales. There is no sudden break between quantum and classical worlds. For you, this reinforces stability. The world does not change rule abruptly beneath experience. We don't need to resolve emergence here. The continuity is already present. From this point, the landscape remains open, ready to unfold further, without pressure or demand. Nothing from earlier needs to be gathered or reviewed. The ideas are already moving forward on their own. Imagine a carefully controlled experiment, isolated from noise, temperature shifts, and vibration. The goal is not complexity, but clarity. In quantum physics, isolation is essential for observing delicate quantum behavior. When a system is well isolated, its wave function evolves with minimal disturbance. This allows quantum properties like superposition and interference to remain intact long enough to study. This is not because quantum effects are unusual. It is because they are easily overwhelmed by interactions with the environment. This matters because it explains why quantum behavior feels hidden in daily life. It is not absent, only masked. For you, this reframes rarity. The quantum world is not distant or exotic. It is simply quiet. That quiet presence doesn't require attention. It remains steady beneath experience as we continue. That sense of quiet persistence carries us forward. Nothing has changed direction. Picture a system prepared the same way again and again, with careful repetition. In quantum mechanics, preparation matters deeply. The way a system is prepared determines the probabilities of future outcomes. Different preparations can lead to very different statistical results, even if the system itself appears similar. This means quantum states are not just descriptions, they are records of physical preparation. This matters because it grounds abstraction in practice. Quantum states reflect real procedures, not imagined conditions. For you, this reinforces clarity. What is known about a system comes from how it was formed and handled. That connection doesn't need emphasis. It holds naturally, supporting the structure of the theory. Nothing has been left behind. We're simply shifting attention slightly. Imagine a system changing smoothly, with no sudden jumps in its internal description. Between measurements, quantum systems evolve continuously. Their wave functions change smoothly over time according to deterministic rules. This continuity means that probabilities shift gradually. There are no spontaneous breaks or leaps until interaction occurs. This matters because it preserves coherence. Quantum systems behave predictably until they are disturbed. For you, this introduces calm regularity. Even in a probabilistic framework, change is not abrupt or chaotic. That steadiness can remain in the background. It doesn't need to be held actively as we move on. The pace remains even and unforced. We're still within the same conceptual space. Picture a system interacting weakly, exchanging only small amounts of information. In quantum physics, weak measurements allow partial information to be gathered without fully collapsing a system's state. They disturb the system less than strong measurements. This shows that measurement is not all or nothing. Interaction strength matters. This matters because it refines the idea of observation. Outcomes depend on how systems interact, not on a single dramatic event. For you, this softens the notion of collapse. Quantum change can be gradual and layered. That nuance doesn't need to be resolved. It can remain quietly present as we continue forward. Nothing here requires tightening or closure. The continuity remains intact. Imagine a set of rules that apply universally, regardless of scale or setting. Quantum mechanics respects symmetry principles. Symmetries in space and time lead directly to conservation laws. This connection is precise and mathematical. For example, uniformity in time implies conservation of energy. These principles hold in quantum systems just as they do in classical ones. This matters because it preserves unity. The same deep structures govern nature everywhere. For you, this maintains trust. Quantum theory does not fragment reality. It extends existing order. That extension doesn't ask for attention. It supports the framework quietly as we move onward. The setting remains calm and open. Nothing has accelerated. Picture particles exchanging forces through subtle, momentary interactions. In quantum field theory, particles are excitations of underlying fields. Fields exist everywhere in space. Particles appear as localized disturbances within them. This shifts the picture of matter. Fields are fundamental. Particles are manifestations. This matters because it unifies forces and matter within a single framework. Interactions become field-based processes. For you, this reframes substance. What feels solid emerges from activity, not static building blocks. That idea can remain gentle and incomplete. Its structure is already sufficient to carry forward. As this segment continues, nothing calls for a conclusion. Imagine layers of description working together, each one accurate within its scope. Quantum physics does not demand that everyday intuition be discarded. It explains where intuition applies and where it gradually gives way. This matters because it preserves continuity of understanding. Different descriptions coexist without conflict. For you, this allows ease. You're not required to replace one view of the world with another. The deeper description simply rests beneath experience, supporting it quietly. And from here, the landscape remains open, ready to unfold further, without pressure and without demand. Nothing needs to be retrieved from earlier segments. The path has been continuous the whole time. Imagine a long sequence of experiments performed in different countries using different equipment by people who never meet. Quantum physics is remarkable for its consistency. When experiments are repeated under the same conditions, the statistical results agree across laboratories and decades. This reproducibility is one of the strongest features of the theory. The equations do not adapt to the experimenter, they apply uniformly, regardless of who performs the measurement. This matters because it grounds quantum physics as a shared description of nature, not a contextual or observer-dependent one. For you, this offers quiet reassurance. The ideas here are not fragile interpretations, they are stable patterns confirmed repeatedly. That stability doesn't need reinforcement, it holds naturally, and we can move forward without effort. That sense of reliability carries forward unchanged. The setting remains steady. Picture a clockwork mechanism, each gear influencing the next. In quantum theory, interactions are local. Systems influence one another only through direct physical contact or exchange. Even entanglement does not violate this. No usable signal travels instantaneously. Causality is preserved. The structure of space-time remains intact. This matters because it aligns quantum physics with relativity at the level of information transfer. The universe does not permit hidden shortcuts. For you, this maintains coherence. Despite its unfamiliar features, quantum physics does not undermine the basic order of cause and effect. That order doesn't ask for attention. It remains quietly present as we continue along the same path. Nothing has shifted abruptly. We are still within the same conceptual rhythm. Imagine a system that can be described in more than one mathematical way. Quantum mechanics allows multiple equivalent formulations. The wave mechanics approach and the matrix mechanics approach produce identical predictions. Though they look different on paper, they describe the same physical reality. This matters because it shows that the theory is not dependent on a single representational language. Its structure is deeper than its notation. For you, this reduces pressure. Understanding does not require loyalty to one symbolic picture. The consistency exists beneath representation. We can let the mathematics remain in the background and continue gently onward. The pace remains slow and even, no summary is forming. Picture a system transitioning smoothly from one description to another. At large scales, quantum predictions blend seamlessly into classical ones. This correspondence is precise. As systems grow larger or warmer, quantum effects average out. Classical physics is recovered naturally, not imposed artificially. This matters because it shows that quantum theory contains classical theory as a limiting case. Nothing is discarded. For you, this preserves familiarity. The world you recognize is not separate from deeper rules. That continuity can remain unspoken. It already supports the experience of everyday reality as we move on. Nothing new needs to be held tightly. We're simply adjusting focus again. Imagine a delicate balance maintained automatically. Quantum systems follow strict mathematical constraints. Not every state is allowed. The rules define what is possible and what is forbidden. These constraints are not arbitrary. They arise from symmetry, structure, and the form of the equations themselves. This matters because it limits speculation. Quantum physics is not open-ended imagination. It is tightly regulated by consistency. For you, this brings calm precision. The theory does not drift. It stays anchored to internal logic. That anchoring doesn't require inspection. It holds the structure quietly in place as we continue. The atmosphere remains unchanged. We are still within the same steady flow. Picture information moving through a system, being redistributed rather than destroyed. In quantum physics, information is conserved. It may spread out or become inaccessible, but it is not erased by physical processes. This principle shapes modern physics deeply. It guides how systems evolve and constrains possible theories. This matters because it preserves continuity in time. The past is not eliminated, it is transformed. For you, this reframes loss. Even when details fade from access, they remain part of the physical story. That idea doesn't need resolution. It can rest quietly, still and complete enough to carry forward. As this segment continues, nothing is being wrapped up. Imagine layers of quiet structure supporting everything that appears solid. Quantum physics describes those layers with restraint and precision. It does not seek to astonish, it seeks to account. This matters because it keeps wonder grounded. The theory remains descriptive, not performative. For you, this allows ease of listening. There is no test of comprehension here, only exposure to a stable framework. We don't need to draw meaning from that now. The structure is already doing its work, and from this point, the landscape remains open, continuing forward, without pressure and without demand. Nothing needs to be gathered from before. The movement has been steady the entire time. Imagine a quiet diagram drawn on a page. Lines intersect gently, not to decorate, but to show relationships. In quantum physics, states are represented mathematically as vectors in an abstract space called Hilbert space. This space is not physical. It does not describe location or distance. It describes relationships between possible states. Each possible condition of a system corresponds to a point in this space. The mathematics allows probabilities to be calculated through geometric relationships. This matters because it reframes description. Quantum theory does not picture objects directly. It maps possibilities with precision. For you, this eases visualization. You don't need to imagine particles moving. You can imagine relationships being structured. That structure doesn't ask to be pictured fully. It works quietly in the background as we continue. That abstract space remains with us, without becoming heavier. Picture two directions that are perfectly perpendicular. They share a space, but do not overlap. In quantum mechanics, some states are orthogonal. This means they are completely distinct. If a system is in one orthogonal state, it has zero probability of being found in the other. Orthogonality allows clear distinctions. It defines when outcomes exclude one another. Measurement outcomes are associated with sets of orthogonal states. This matters because it gives quantum theory a clean internal logic. Not everything blends. Some possibilities remain fully separate. For you, this restores clarity. Even within probability, there are firm boundaries. Those boundaries don't need defending. They are built into the structure itself, and we can move on gently. Nothing has been complicated further. We're simply turning the same object slightly. Imagine rotating a shape and noticing that its appearance changes, even though the shape itself does not. In quantum physics, changing how a system is measured changes which properties are well defined. Different measurement choices correspond to different mathematical bases in Hilbert space. The system itself does not change, only the description does. Each basis highlights different features. This matters because it explains why certain properties cannot be known simultaneously. They correspond to incompatible descriptions. For you, this reframes limitation. What can be known depends on perspective, not deficiency. That dependence doesn't imply confusion, it reflects structure. We can let that remain quietly present as we continue. The pace remains slow and even. Nothing asks to be resolved. Picture a smooth transformation, where one description turns gradually into another. Quantum states can be transformed using precise mathematical operations. These operations preserve total probability. They rotate states within Hilbert space without destroying information. Such transformations describe how systems respond to forces, fields, and interactions. They are reversible in principle. This matters because it preserves symmetry. Quantum evolution respects balance and structure. Nothing arbitrary is introduced. For you, this brings calm order. Change does not mean loss, it means reconfiguration. That idea can remain light. The transformations already obey their rules without attention from us. Nothing new needs emphasis. The framework is holding on its own. Imagine a set of rules that constrain movement without dictating paths. In quantum mechanics, operators represent observables like energy or momentum. Each operator has a set of allowed values. These values emerge from the mathematics itself. The system does not choose them freely. They are determined by structure. This matters because it limits outcomes naturally. Quantum results are not selected arbitrarily. They arise from defined constraints. For you, this reinforces predictability. Even when outcomes vary, the space of variation is fixed. That containment doesn't feel restrictive. It creates reliability, and we can continue onward without effort. The setting remains unchanged. The ideas continue unfolding quietly. Picture a system interacting briefly, then continuing on its way. In quantum theory, interactions are described by coupling between systems. The strength of coupling determines how much states influence one another. Weak coupling produces subtle effects. Strong coupling produces dramatic change. The rules remain the same. This matters because it explains why some interactions dominate behavior while others barely register. For you, this provides scale. Not every interaction carries equal weight. Influence is graded, not absolute. That gradation doesn't require management. It exists naturally within the equations as we move forward. As this segment continues, nothing is being concluded. Imagine a framework that remains open, able to describe new systems without changing its foundations. Quantum mechanics has remained stable while being applied to atoms, solids, fields, and information systems. Its structure adapts without rewriting itself. This matters because it shows resilience. The theory is not fragile. It accommodates growth without fracture. For you, this allows trust without effort. What you're hearing is not provisional language. It's a stable, descriptive core. We don't need to extract meaning from that now. The structure continues quietly, ready to support whatever comes next without pressure and without demand. Nothing needs to be recovered or restated. The motion has remained continuous throughout. Imagine a system observed repeatedly, each observation gentle and precise. In quantum physics, repeated measurements can influence future outcomes. If the same property is measured frequently enough, the system's evolution can be altered. This effect is known as the quantum Zeno effect. By interacting with the system repeatedly, certain transitions are suppressed. The system remains in its initial state longer than it otherwise would. This matters because it shows that measurement is an active process. Interaction does not merely reveal change, it can shape it. For you, this reframes observation. Looking is not passive at fundamental scales. That influence doesn't need to be emphasized. It rests quietly within the rules as we continue. That quiet influence remains present as we move forward. Picture a system allowed to evolve freely, then gently constrained. Quantum dynamics depend on interaction history. Past interactions affect future probabilities. This dependence is encoded mathematically in the system's state. The system does not forget immediately. Its evolution reflects prior coupling. This matters because it gives quantum systems a kind of continuity. They carry traces of interaction forward in time. For you, this suggests persistence without memory in the usual sense. The past shapes the present through structure, not recollection. That shaping doesn't require attention. It happens automatically as the system evolves. Nothing is shifted abruptly. The pace remains unhurried. Imagine information spreading outward, becoming harder to gather back together. In quantum systems, entanglement can spread through interactions with additional particles. This process distributes correlations across systems. Once spread, these correlations become difficult to reverse. The information is still present, but no longer localized. This matters because it explains why complex quantum systems are hard to control. Order disperses into collective structure. For you, this offers perspective. Complexity arises naturally from simple interactions repeated many times. That emergence doesn't need explanation now. The process itself is already sufficient to carry us forward. The environment remains calm and open. Nothing is being concluded. Picture a system interacting with heat, slowly exchanging energy. Temperature influences quantum behavior. At higher temperatures, thermal motion disrupts quantum coherence. At lower temperatures, quantum effects persist longer. This is why many quantum experiments are conducted near absolute zero. Thermal noise is reduced, allowing fragile states to survive. This matters because it ties quantum behavior to ordinary physical conditions. Heat becomes a controlling factor. For you, this grounds abstraction. Quantum behavior responds to familiar variables like temperature. That connection doesn't need emphasis. It remains quietly reliable as we continue. Nothing has accelerated. The rhythm remains steady. Imagine a system interacting with light, absorbing and emitting energy. In quantum mechanics, emission and absorption occur through discrete transitions. An atom changes energy levels by exchanging quanta with radiation. These transitions follow strict selection rules. Not every transition is allowed. This matters because it explains why spectra are precise and repeatable. The rules govern interaction tightly. For you, this provides reassurance. Even microscopic change follows structure. That structure doesn't demand attention. It remains intact on its own as we move forward. The scene remains quiet and controlled. Nothing asks to be wrapped up. Picture a system influenced by an external field. Quantum systems respond predictably to electric and magnetic fields. These fields alter energy levels and shift probabilities. This interaction allows precise control. External fields can guide behavior without direct contact. This matters because it enables manipulation of quantum systems in practice. Control does not require forceful intervention. For you, this shows how subtle influence can produce reliable change. That influence doesn't need further elaboration. It is already woven into the theory as we continue. As this segment continues, nothing is being finalized. Imagine a framework flexible enough to describe change without losing order. Quantum physics accounts for interaction, history, environment, and control within a single consistent structure. This matters because it preserves coherence as complexity increases. The rules do not fragment. For you, this supports ease of listening. The ideas do not compete with one another. They accumulate quietly. We don't need to extract meaning yet. The framework is already holding, and from here, the landscape remains open, continuing forward without pressure and without demand. Nothing needs to be retrieved from earlier. The continuity has been unbroken all along. Imagine a system that can be described in more than one complementary way, each description complete on its own. In quantum physics, physical properties are represented by mathematical operators. Different operators correspond to different measurable quantities. Some of these operators do not commute, meaning the order of measurement matters. This non-commutation is not a technical detail. It reflects a fundamental feature of nature. Certain properties cannot be sharply defined together. This matters because it explains why quantum limitations are structural, not practical. For you, this reframes constraint. Limits arise from deep consistency, not from missing tools. That consistency doesn't require inspection. It remains quietly active as we continue forward. That structural consistency remains in place. Nothing has shifted direction. Picture two measurements taken in succession, each influencing what follows. When quantum operators do not commute, measuring one property changes the statistical distribution of the other. The system is altered by the first interaction. This does not introduce disorder. It introduces dependence on sequence. The order of events becomes meaningful. This matters because it replaces the idea of passive measurement. Interactions leave traces. For you, this introduces subtle causality. What happens first shapes what can happen next. That shaping doesn't require effort to track. It is already built into the structure as we move on. Nothing has become heavier. We are still within the same calm framework. Imagine a system described by probabilities that must always add to one. In quantum mechanics, total probability is conserved over time. No matter how probabilities shift internally, their sum remains fixed. This conservation ensures consistency. Outcomes redistribute, but none appear from nothing. This matters because it guarantees completeness. The theory accounts for all possibilities within its scope. For you, this brings quiet assurance. Nothing leaks out of the description. Everything remains contained. That containment doesn't feel restrictive. It simply holds the structure together as we continue. The pace remains even, no resolution is approaching. Picture a system interacting with noise, yet retaining a recognizable pattern. Quantum systems can be influenced by random external disturbances. Despite this, their statistical behavior remains predictable. Noise changes outcomes, but not the rules governing them. The underlying structure persists. This matters because it shows robustness. Quantum theory tolerates imperfection without losing coherence. For you, this suggests resilience. Order does not require ideal conditions to exist. That resilience can remain unspoken. It already supports the framework as we move forward. Nothing new needs to be emphasized, and the continuity holds. Imagine a system transitioning between two allowed configurations. In quantum mechanics, transitions occur when systems interact. They are governed by precise probabilities calculated from the system's state. No transition happens without cause. Interactions provide the pathway. This matters because it preserves causality. Change does not arise spontaneously. For you, this maintains coherence. Even at small scales, events follow from interaction. That coherence doesn't require vigilance. It is already embedded as we continue onward. The environment remains calm. Nothing is being closed. Picture a system exchanging information without exchanging energy. In quantum physics, information and energy are related but distinct. Some interactions transfer information with minimal energy cost. This matters because it allows subtle influence. Systems can become correlated without dramatic exchange. For you, this introduces nuance. Impact does not always require force. That nuance can remain light. It does not need to be carried actively as we move on. As this segment continues, nothing is being concluded. Imagine a framework capable of describing both stability and change without contradiction. Quantum physics balances fixed structure with flexible outcome. Its rules remain constant while results vary. This matters because it preserves intelligibility. Variation does not undermine law. For you, this allows ease of understanding. Nothing here demands certainty or resolution. The framework continues quietly, holding complexity without strain, and from this point, the landscape remains open, ready to extend further, without pressure and without demand. Nothing needs to be brought forward deliberately. The continuity has never broken. Imagine a system described not by certainty, but by a smooth distribution of possibilities. In quantum physics, probability amplitudes can be complex numbers, meaning they have both magnitude and phase. The phase does not affect probability directly, but it influences how amplitudes combine. When amplitudes meet, their phases determine whether they reinforce or cancel one another. This is why interference patterns appear. This matters because it shows that unseen features influence outcomes. What cannot be measured directly still shapes what is observed. For you, this adds depth without complication. Not everything important is immediately visible. That depth doesn't need exploration now. It already supports the behavior we see as we continue onward. That quiet influence remains present. Nothing has shifted in tone or direction. Picture a system evolving smoothly, guided by an internal rhythm. In quantum mechanics, symmetry plays a central role. Symmetries describe transformations that leave physical predictions unchanged. Rotating a system, shifting it in time, or translating it in space often changes nothing essential. These symmetries constrain the equations and determine allowed behaviors. This matters because it reveals why laws of physics appear uniform everywhere. They are built on invariance. For you, this provides reassurance. Nature does not reinvent its rules from place to place. That uniformity doesn't require attention. It remains quietly embedded as we move forward. Nothing has become more demanding. we are still moving evenly. Imagine a system prepared carefully, then allowed to interact freely. In quantum physics, preparation and evolution are distinct stages. The initial state sets probabilities, but the subsequent evolution follows fixed equations. This separation clarifies responsibility. Preparation determines what is possible. Evolution determines how possibilities unfold. This matters because it structures explanation. Different questions are answered by different parts of the theory. For you, this reduces confusion. Not everything happens at once. Processes unfold in stages. That staging doesn't need emphasis. It organizes understanding quietly as we continue. The pace remains slow and steady. No conclusion is forming. Picture a system that can be described using alternative variables, each revealing something different. In quantum mechanics, the same system can be expressed in position space or momentum space. These descriptions are connected mathematically through precise transformations. Neither description is more real. Each highlights different features. This matters because it shows that description depends on context, not on preference. For you, this allows flexibility. Understanding can come from more than one angle without contradiction. That flexibility doesn't need to be managed. It exists naturally within the framework as we move on. Nothing is accelerated. The structure remains intact. Imagine a system responding predictably to a gentle change in conditions. In quantum physics, small changes produce proportional effects. This linear response ensures stability. Sudden divergence does not occur without strong interaction. This matters because it preserves control. Quantum systems are sensitive but not fragile by default. For you, this reframes delicacy. Sensitivity does not imply instability. That reassurance doesn't require reinforcement. It already supports the framework quietly as we continue. The atmosphere remains calm. Nothing is being finalized. Picture a system that can be scaled up without losing coherence in its rules. Quantum mechanics applies to single particles and to collections of many particles. As systems grow larger, their collective behavior becomes smoother. The same equations still apply, only the interpretation shifts. This matters because it preserves unity. There is no new physics required simply because a system becomes large. For you, this maintains continuity. The familiar world grows naturally from deeper description. That growth doesn't need explanation now. It is already supported by structure as we move forward. As this segment continues, nothing is being tied together. Imagine a framework that allows both precision and openness. Quantum physics does not demand that outcomes be fixed in advance. It demands only that probabilities be calculated consistently. This matters because it balances freedom and rule. Variation exists within constraint. For you, this creates ease of listening. There is no requirement to resolve uncertainty. The framework continues quietly, holding possibility without strain, and from here, the landscape remains open, ready to extend further, without pressure and without demand. Nothing needs to be recalled or reinforced. The continuity has remained unbroken throughout. Imagine a system described not by objects, but by relationships between quantities. In quantum physics, observables are linked through precise mathematical relations. These relations define what can be known together and what cannot. They are not imposed externally. They emerge from the structure of the theory itself. This means limits on knowledge are not flaws in measurement. They are reflections of internal consistency. This matters because it grounds uncertainty in order rather than deficiency. The rules protect coherence. For you, this reframes limitation. What cannot be known simultaneously is not missing, it is defined. That definition doesn't ask for agreement, it already holds its place as we continue gently forward. That sense of structure remains steady. Nothing has shifted in tone or direction. Picture a system interacting with many others, each interaction small on its own. In quantum mechanics, complex behavior emerges from repeated simple interactions. There is no added rule for complexity. The same principles apply again and again. As interactions accumulate, patterns form that are not obvious from a single event. This matters because it explains how richness arises without complication. The theory remains compact while outcomes diversify. For you, this softens complexity. The world does not require layered rules to become detailed. That emergence doesn't need emphasis. It is already happening continuously beneath experience. Nothing has been tightened or resolved. We're simply shifting attention once more. Imagine a system described probabilistically, yet constrained by strict boundaries. In quantum physics, allowed states are limited by mathematical conditions. Not every conceivable state is permitted. The theory selects only those that remain internally consistent. This matters because it prevents contradiction. Possibility is not unlimited, it is structured. For you, this restores balance. Freedom exists, but it operates within form. That form doesn't need inspection. It quietly shapes outcomes as we continue onward. The pace remains unhurried. No summary is forming. Picture a system evolving reversibly, at least in principle. Quantum equations allow time reversal. If conditions were perfectly controlled, a system could retrace its evolution. This reversibility exists until interaction with the environment introduces irreversibility. This matters because it separates fundamental laws from practical experience. The equations remain symmetric even when outcomes do not. For you, this clarifies direction. Irreversibility arises from interaction, not from the core rules. That distinction can remain light. It already supports understanding without effort. Nothing has accelerated. The structure remains calm. Imagine a system responding to a precisely tuned influence. In quantum physics, resonance occurs when external influence matches a system's natural frequency. At resonance, responses are amplified. This principle governs transitions, absorption, and emission. It allows selective interaction without broad disruption. This matters because it shows how precision creates efficiency. Small influences can have large effects when matched correctly. For you, this demonstrates alignment. Effectiveness does not require force, only compatibility. That idea doesn't need expansion. It is already complete enough to carry forward. The atmosphere remains steady. Nothing is being closed. Picture information flowing through many degrees of freedom. In quantum systems, information can be spread across correlations. It may not be stored in one place. Instead, it exists relationally. This makes retrieval difficult, but not destruction possible. This matters because it shapes how complexity and irreversibility appear. Information disperses rather than vanishing. For you, this reframes loss again. Absence does not mean erasure. That reframing doesn't ask to be resolved. It can rest quietly as we continue onward. As this segment continues, nothing is being tied together. Imagine a framework capable of describing both isolation and interaction without contradiction. Quantum physics handles both states with the same rules, only conditions change. This matters because it preserves unity. The theory does not fracture when context shifts. For you, this supports ease. Understanding does not require switching frameworks. The structure continues quietly, holding both separation and connection without strain. And from here, the landscape remains open, ready to extend further, without pressure and without demand. Nothing needs to be carried forward consciously. The progression has been steady and uninterrupted. Imagine a system described not by fixed outcomes, but by a rule for generating them. In quantum physics, the formalism provides a complete recipe for prediction. Given a state and a measurement, the probabilities of all possible outcomes can be calculated exactly. There is no missing step in this process. The uncertainty lies only in which outcome occurs, not in how outcomes are determined statistically. This matters because it defines completeness. Quantum mechanics does not lack predictive power. It uses a different kind of prediction. For you, this reframes expectation. Knowing how often replaces knowing which one. That replacement doesn't reduce clarity. It simply shifts the level at which certainty lives as we continue gently onward. That sense of structured prediction remains intact. Nothing has shifted direction. Picture a system interacting briefly, then separating again. In quantum mechanics, interactions leave correlations behind. Even after systems part ways, their shared history influences future statistics. This does not require continuous contact. The correlation persists as a consequence of prior interaction. This matters because it gives interactions duration. Effects are not confined to the moment of contact. For you, this introduces continuity across time. Past encounters shape future possibility without ongoing force. That continuity doesn't need emphasis. It is already embedded quietly in how the theory unfolds. Nothing has become more abstract. The pace remains even. Imagine a system described by limits that cannot be exceeded. In quantum physics, uncertainty relations place lower bounds on joint knowledge. These bounds are fixed and universal. No refinement of technique can push beyond them. They define the shape of what is knowable. This matters because it stabilizes description. The theory does not change with improved instruments. For you, this provides reassurance. Limits are not moving targets. They are part of the framework itself. That stability doesn't require attention. It remains quietly in place as we continue. The environment remains calm and open. Nothing is being resolved. Picture a system evolving smoothly, even when outcomes are unpredictable. In quantum mechanics, evolution equations are continuous and deterministic. The randomness appears only at measurement. This separation preserves clarity. Dynamics and outcomes are governed by different rules within the same theory. This matters because it prevents confusion. Indeterminacy does not infect everything. For you, this restores balance. Not all uncertainty is everywhere. That balance doesn't ask for agreement. It simply holds, quietly, supporting the overall structure. Nothing new needs emphasis. The continuity remains intact. Imagine a system interacting repeatedly with similar environments. In quantum physics, repeated interactions produce predictable statistical effects. Noise averages out. Patterns remain. This matters because it shows robustness. Quantum predictions survive imperfection. For you, this allows trust. Precision does not depend on ideal conditions to exist meaningfully. That trust doesn't need reinforcement. It is already supported by repetition and consistency. We can move forward without carrying it actively. The pace remains slow and steady. Nothing is being closed. Picture a framework that does not specify what must be observed, only how observation behaves. Quantum mechanics does not prescribe which measurements should be made. It describes how results behave once a measurement is chosen. This matters because it preserves neutrality. The theory does not privilege questions. For you, this creates openness. Different inquiries are equally valid within the same structure. That openness doesn't need explanation. It already exists quietly as we continue onward. As this segment continues, nothing is being concluded. Imagine a system whose description remains consistent no matter how often it is applied. Quantum physics has been tested across scales, materials, and conditions. its rules continue to hold. This matters because it shows durability. The framework does not erode with use. For you, this supports calm listening. There is no hidden instability here. We don't need to extract meaning now. The consistency is already doing its work, and from here, the landscape remains open, continuing forward without pressure and without demand. Nothing needs to be retrieved from earlier segments. The progression has remained smooth and uninterrupted. Imagine a system described not by certainty, but by a landscape of allowed possibilities. In quantum physics, probabilities are not assigned arbitrarily. They are calculated using a strict mathematical rule known as the Born rule. This rule states that the probability of an outcome is given by the square of the wave function's amplitude. This is not an optional add-on. It is the bridge between abstract mathematics and measurable results. This matters because it anchors quantum theory to experiment. Without this rule, the equations would remain detached from physical observation. For you, this provides quiet reassurance. There is a clear and consistent link between calculation and outcome. That link doesn't require attention. It has already been working reliably as we continue forward. That sense of grounding remains intact. Nothing has shifted in direction. Picture a system interacting weakly, then more strongly, with the same environment. In quantum mechanics, the strength of interaction directly affects how probabilities change. Stronger coupling leads to faster redistribution of outcomes. Weaker coupling allows coherence to persist longer. This relationship is continuous, not abrupt. There is no sharp boundary between quantum and classical behavior. This matters because it explains gradual transition. Behavior changes smoothly with conditions. For you, this restores continuity. Nature does not switch modes suddenly. It adjusts. That adjustment can remain quiet. It is already embedded in how the equations respond to change. Nothing has become heavier or more abstract. We're simply turning the same structure again. Imagine a system whose description can be simplified without losing accuracy. In quantum physics, effective theories are often used. When details are irrelevant at a given scale, they can be averaged out. The resulting description remains accurate for the phenomena of interest. This does not discard information carelessly. It respects which details matter at which scale. This matters because it allows understanding without unnecessary complexity. Precision is preserved where it counts. For you, this provides ease. You're not required to carry every detail to understand behavior meaningfully. That simplification doesn't reduce truth, it refines focus as we continue onward. The pace remains even and unforced. No conclusion is forming. Picture a system described from the outside without tracking every internal motion. In quantum mechanics, open systems are common. They exchange energy or information with their surroundings. These exchanges can be modeled without specifying the full environment. Statistical descriptions capture the essential effects. This matters because it makes real systems describable. Perfect isolation is not required for understanding. For you, this grounds abstraction again. The theory is built to handle imperfection. That capability doesn't need emphasis. It already supports application beyond idealized cases as we move forward. Nothing has shifted abruptly. The structure remains calm. Imagine a system evolving under the influence of steady constraints. In quantum physics, constraints define allowed motion. Conservation laws, symmetries, and boundary conditions shape evolution continuously. These constraints do not stop change, they guide it. This matters because it preserves predictability. Even when outcomes vary, they do so within a fixed framework. For you, this maintains coherence. Change does not imply loss of structure. That coherence doesn't ask for attention. It is already holding quietly as we continue. The atmosphere remains steady and open. Nothing is being wrapped up. Picture a system interacting through fields without direct contact. In quantum field descriptions, interactions are mediated by fields that permeate space. Particles influence one another by altering these fields locally. This avoids action at a distance. Influence propagates through defined structure. This matters because it preserves locality. Even subtle quantum effects respect spatial organization. For you, this reinforces order. Influence moves through connection, not instant reach. That order doesn't need explanation. It is already woven into the framework as we continue onward. As this segment continues, nothing is being concluded or summarized. Imagine a theory capable of refinement without losing its foundation. Quantum physics continues to be extended into information, materials, and cosmology without altering its core principles. This matters because it shows stability. Growth does not require replacement. For you, this supports quiet trust. The structure you're hearing is not provisional scaffolding. We don't need to draw meaning from that now. The stability is already present, and from here, the landscape remains open, ready to continue unfolding, without pressure and without demand. Nothing needs to be gathered from what came before. The continuity has carried itself all along. Imagine a framework that does not aim to describe what reality feels like, but how outcomes reliably relate. Quantum physics is not a theory of experience. It is a theory of relationships between measurements. It connects preparation, interaction, and outcome through precise mathematical rules. It does not claim to describe what a particle really is between interactions. It describes what can be said consistently about results. This matters because it defines the theory's restraint. Quantum mechanics does not overreach. It speaks only where it can speak accurately. For you, this can feel grounding. There is no hidden message to decode, only a structure that stays within its limits. That restraint can remain quietly present as we move forward. That sense of restraint remains steady. Nothing has shifted direction. Picture a map that shows connections, not terrain texture. In quantum physics, the theory does not specify a single interpretation by necessity. Multiple interpretations exist, all producing identical experimental predictions. These interpretations differ in how they talk about the mathematics, not in what the mathematics delivers. The measurable results remain unchanged. This matters because it separates prediction from storytelling. The theory itself does not depend on a preferred narrative. For you, this removes pressure. You're not required to adopt a worldview to understand the science. The facts remain intact regardless of interpretation. That stability can rest quietly as we continue. Nothing has become more abstract. We are still within the same calm frame. Imagine a tool that works reliably without needing explanation of its internal meaning. Quantum mechanics functions this way in practice. Engineers and scientists use its equations to design transistors, lasers, and sensors without resolving interpretive questions. The predictive machinery operates independently of philosophical preference. This matters because it anchors quantum physics firmly in utility and verification. The theory earns trust through use. For you, this can feel reassuring. Understanding does not require philosophical closure. Function precedes interpretation. That separation doesn't need to be resolved. It already allows the theory to stand on its own as we move on. The pace remains slow and unforced. Nothing is being concluded. Picture a system that behaves consistently no matter how many times it is tested. Quantum mechanics has been subjected to extreme experimental scrutiny. Its predictions continue to hold across decades of increasingly precise tests. No confirmed deviation has been found within its domain of applicability. This matters because it establishes confidence. The theory is not fragile, it withstands pressure. For you, this reinforces calm listening. What you're hearing is not speculative. It is one of the most reliable frameworks ever developed in science. That reliability doesn't need emphasis. It is already built into the structure as we continue forward. Nothing new needs to be held tightly. The continuity remains intact. Imagine a description that becomes simpler, not more complex, as understanding deepens. Quantum physics replaces many classical assumptions with fewer, more precise principles. It removes unnecessary detail in favor of consistent structure. This matters because it reduces conceptual clutter. The theory does not grow by accumulation. It grows by refinement. For you, this can feel like relief. Understanding does not require stacking ideas endlessly. It often requires letting some go. That refinement can remain gentle. Nothing needs to be discarded actively as we move on. The atmosphere remains steady and open. Nothing is being wrapped up. Picture a framework that remains valid even when its limits are acknowledged. Quantum mechanics does not claim to describe gravity at all scales. It does not claim to explain everything. Its boundaries are known and respected. This matters because it preserves integrity. A theory that knows its limits remains trustworthy within them. For you, this supports calm confidence. Unanswered questions do not weaken what is answered. That balance doesn't require resolution. It simply holds, allowing the theory to remain precise without overreach. As this segment continues, nothing is being closed or summarized. Imagine a foundation that remains quietly in place while many structures are built upon it. Quantum physics serves this role across modern science and technology. Its principles continue to support new applications without losing coherence. This matters because it shows endurance. The framework does not depend on novelty to remain relevant. For you, this allows ease. There is nothing here to finish or conclude, only a stable ground that remains available. The ideas do not need to resolve themselves now. They can remain open, unfinished in the best sense, continuing quietly, without pressure and without demand. Nothing here needs to settle into a final shape. Some of these ideas may still be moving quietly in the background, and others may simply pass through without leaving a trace. Both are completely fine. Quantum physics does not ask to be held tightly, or even fully understood all at once. It continues whether we attend to it or not. You can remain alert, or let your attention soften, without losing anything essential. There is nothing to remember, nothing to resolve, and nothing that needs to be complete. The ideas can stay unfinished, available to return to later or not at all, while the world they describe carries on, calmly and reliably, on its own.